The universe is a symphony of invisible forces. From the spark of lightning to the glow of distant stars, electromagnetism weaves the fabric of reality. For over a century, physicists have sought to decode its quantum secrets. But simulating these forces has been like trying to capture starlight in a bottle until now. Einstein dreamed of a unified theory. Feynman sketched diagrams to explain particle interactions. Today, a new generation of scientists is wielding a revolutionary tool, a quantum computer that breathes life into equations once deemed unsolvable. This is not just a breakthrough, it's a portal to the quantum universe. Classical computers built our digital age. But when it comes to simulating quantum forces like electromagnetism, they hit a wall. Why? Because the equations governing particles and fields are exponentially complex. Imagine tracking every electron on a cosmic chessboard, each move entangled with an invisible force field. Classical machines drown in the math. Even the world's fastest supercomputer can't model real-time particle interactions into D or 3D. It's like predicting a hurricane. One raindrop at a time, we've hit the limits of classical physics. To go further, we need to think quantum. Enter the trap, I don't quantum computer. Here, atoms suspended in electric fields become quantum laboratories. Their secret? Qudits, the unsung heroes of this story, while qubits are like simple switches. Qudits are multi-state powerhouses. Imagine a piano key that can play 10 notes at once. For simulating high-dimensional forces like electromagnetism, Qudits are revolutionary. Using precision lasers, scientists engineer these ions into mixed-dimensional systems. Matter becomes qubits. Force fields become Qudits. Together, they form a quantum canvas to paint the laws of nature, the team's mission. Simulate 2D quantum electrodynamics cue the rules governing electrons, light, and their dance. To do this, they encoded a single plaquette, the universe's smallest building block of spacetime. Each corner hosts a qubit representing electrons or positrons. The links between them? A qutrit, a 3-level qubit encoding the electric field strength from negative to positive. This tiny grid holds the keys to cosmic scale physics. Gauss's law, the rule that TIs matter to force fields, is baked into the hardware. We're not just simulating physics. We're embodying it to find the system as ground state, its lowest energy configuration. The team composed a variational quantum eigensolver, VEEQ. Think of it as a quantum maestro, tuning parameters until the orchestra plays in harmony. Using hybrid qubit-qudit gates, the circuit weaves matter and forces into a single quantum state. A classical computer then refines the result, closing the loop between old and new computing. Every run teaches us something new. It's like watching the universe debug itself. The results were staggering. By varying the coupling strength, the dial for how tightly particles interact, they observed the birth of magnetic energy and virtual particles blinking in and out of existence. At weak coupling, magnetic fields dominated. At strong coupling, electric fields roared. And in between, a chaotic tango of particles and forces a window into quantum chaos. This isn't just data. It's the universe's heartbeat, recorded for the first time, but to mirror reality. Precision is key. The team upgraded from qutrits to ququints 5-level Qudits, capturing finer details of force fields. With ququints, truncation errors faded. The simulation grew sharper, revealing how forces behave at different energy scales. It's like upgrading from a flip phone to a 4,000 camera. Every level we add gets us closer to nature's true language, no approximations. The ultimate test? Simulating time itself. Using a Trotter algorithm, the team recreated a quantum quench, a sudden shift in coupling strength, and watched particles erupt from the vacuum. Pairs of electrons and positrons flared into existence, then vanished. Magnetic energy surged and ebbed. For the first time, Humanity witnessed quantum dynamics as they happen. This is just the beginning. Imagine simulating the Big Bang or dark matter collisions in a machine smaller than your desk. The next frontier? Three-dimensional simulations. Scaling up could unlock nuclear physics, superconductors, or even exotic states of matter. From Innsbruck to Waterloo, teams are refining Qudit architectures. Someday, these machines could model black holes or design fusion reactors. We're not just simulating the universe. We're recreating it one qubit at a time. In the quiet hum of trapped ions, we've found a new way to see the unseen. The forces that bind atoms, light the stars, and shape spacetime are no longer hidden. They're here in a lab, waiting to be explored.